So here is the equation we just came up with in the last video for figuring out what is the maximum concentration of a pollutant in a river, and that's based on the initial mass of the chemical per area, the time after the injection or putting in of the chemical into the river, and the longitudinal mixing coefficient. Okay, so this, however, is for conservative chemicals. So this means that this equation can really only be used for chemicals that are only altered by physical processes like dilution. So they're not reduced by biological or chemical processes like decomposition or decay. So these are things like special dyes that you add to rivers to figure out things like the mixing coefficient or the salt solutions that you guys used in lab. But this is not always the case. In fact, it's usually not the case. You've usually got a non-conservative pollution or pollutant or chemical. So this is a pollutant that its concentration is altered by physical but also biological and chemical processes. That is, the concentration will decay over time or be reduced over time by things like decomposition or uptake by plants or animals or just chemical decay. So what do we do in these cases? So for non-conservative chemicals, hopefully this looks somewhat familiar to you. This is the same equation here. And essentially we just add on exponential decay. So we have sort of the mixing or the spread of that chemical, and then we've got exponential loss of that chemical over time. So K is your rate of decay here, and that's in units of 1 over time again. So then this just alters sort of the two main equations. This one is still the same, C max. If you have a non-conservative chemical, you just sort of add on this e to the negative kt, exponential decay. And I just want to point out that if you have a conservative chemical, it would just be, this k would be 0. So you would have e to the 0, which is equal to 1. So this would just end up being 1. Right, and that is all that we're going to talk about in this video.